So first, because I think our approach is from wash, so I should introduce the noise first. Then we're talking about stochastic equations, then intermittency, and then the chaotic characterization. So finals. So first, so what does that mean? So in this room, so we have a temperature. And so white noise means for space, so it's independent, and for time, it's also independent. Then we should construct the space-time white noise first from the white noise. So white noise is a Gaussian process, and it has the covariant functions in this form. And lambda d is the d-dimensional Lebesgue measures. Then white noise has the following properties. Well, first, if you fix omega, then it is finite additive measure. And of course, if you plug in empty states, then it's 0. But it's another measure. But in L2 sense, it's a sigma finite set measure. So that's why I see, so white noise is much rougher than the delta function, because delta function is a measure, but white noise is not. Then to define space-time white noise, then we just take the first coordinate to be our time. Then we can define the WTA, then it's if time is 0, then it's 0. And if we fix time t, then it's a sigma finite, L2t, value summation. And if we fix the set, then this is the mark. So if you know how to construct the integral in SE, then you may convince yourself that we can do that in a similar way. Okay. Then what is current noise? So because the space-time white noise is too rough, so in higher dimension, I say dimension is greater than 2. And if you add space-time white noise, then we won't have solutions. That's why the paper of Dalang invents the current noise. That means time may be rough, but space is fine. So that means we have density for the space. Then they define the current noise to like the generalized functions. So maybe I don't have time to say this rigorously, but you can think that this F is symmetric, non-negative, and non-negative definite. And it should satisfy some conditions. So we consider the following SHE. So here, kappa is the viscosity constant is positive, and the sigma is global Lipschitz continuous, and the F dot is the noise. So in dimension 1, then this F could be a delta function. But in higher dimension, you can consider Fs. So in our work, we consider F to be this convolution type. And then we need to assume that our initial data is non-random, measurable, and uniformly bounded away from infinite limits. The infinite norm is finite. Also, I should mention that the U now is positive. And we know that the most studied case is parabolic Anderson model, which means that sigma U is linear. And here we consider solution to be a Meyer solution. So which means in here we multiply by test functions, then we integrate, and then we move the partial operator to the test functions. And for some spatial test function, we can eliminate some terms. So this become our mild solutions. And the existence and uniqueness of the solution to the SHE is under these conditions. So I'll remind you that the f is the operation function. So what is the level exponent? So it's defined by this way. And we know that since this is convex and 0 and 0, so we know this is non-decreasing. And by their work, they define what is the intermittency, which means this is strictly increasing for p squared than 2. But this is from England and Hoshinemison's paper. But honestly, I don't think that this number is important. Then the next question
is x0 and fixed points. X0.
Yeah. And for any fixed x, you should have this. Then what does the intermittency mean? So we know that we know this is strictly increasing, right? Then if q is strictly greater than p, then we should have this, right? Then we kick L from this interval and consider this x. Then Chebyshev's inequality tells that the probability of this event goes to 0. But if we look at the Q's moment outside the set ET, then we know the order of this is less than the Q's moment of UT. So which means since we know this says the probability of this goes to infinity, it goes to 0. So that means the high peaks dominate the moments. I mean the high peaks contribute the moments. So that's really intermittency. But you may ask, so how to check the intermittency? So if we know that the kappa part is finite, of course this should be finite, otherwise we won't have strict increase. And if you have some C such that gamma bar is greater than 0, then we have the intermittency. So then we should. So intermittency is like if we fix x, then we let t goes to infinity, then you may expect like we should have fluctuations for the solutions. So now we need to introduce some notation. So this means limiting fr over g are is bounded below by constant, and this notation means this is by distributions on both directions, and this means we take log then just say like this. So then Thomas Joseph and Hoshinev-son they prove that so if the sigma is bounded uniformly from 0, then so the suit of this is over this is the check limit is greater than 0. Then if sigma is bounded uniformly away from 0 and infinity, then this should be growth like this order. And in parabolic Anderson model, then we have this. So actually, Laplacian smooth the solutions, but when we add the noise may make the solution worse. So that's kind of a competition between the Laplacian and noise. So if kappa is small, that means we have less ability to smooth our solutions. So that's why you may expect that why we have kappa in here, right? Then Rouse and Turing and Pastel, they asked, so whether we have like these fluctuations. So I didn't mean the power is correct, but should we have fluctuations? If the initial data is a delta function. So the answer is no. So if the initial data is a finite measure, then the solution, so for fixed t, then the solution should be bounded over x. So that means the behavior of the solution is sensitive to the initial data. So like in Higgs equation, if we consider our initial data to be a constant, then if you have a rough source term, then you may expect the fluctuations, right? But in the case of the delta functions, if you are not too unlucky, then the rough source won't appear around the zero. I mean, so that means if that won't happen, then even you have a rough term to affect your solution, then Laplacian will lose it. Then we consider in higher dimension. So actually we consider our initial data to be a constant. Then this is just a technique conditions. And if a sigma is bounded uniform from 0, then we have this. And then if sigma is bounded uniform from 0 and infinity, we get okay. But we should notice that, so there is no kappa. So that means our noise here is relatively smooth. So in parabolic Anderson model, we have the same assumptions. Then we can have this. But here, notice that the constant here really depends on the kappa. The next question is, so if we, since we have the chaotic estimations in dimension 1 and higher, so we just replace the power by this. So in dimension 1, we know that our noise is white space-time white noise, and the scaling is when the size 2/3. And if f is nice, just like we assume, so the size 1/1/2. So is there possible that we can construct the noise so such that we can have this size in between 1/2 and 2/3? So the answer is yes, we can really do that. For in dimension 1, we can find a correction function f6 by this. For every psi is in between. And for higher dimension, precise in 1/2 and 1. So we do this by considering that our correction function is with kernel. So then we have the identities. So here, y alpha is between 0 and the p wedge 2. So alpha is less than d, guarantee that this is a correction function. But if we like to let our SHE has a solution, then alpha should be less than 2. So finally, there is a connection to KPZ equations. So if we know that the solution to our parabolic Anderson model is this, then we can apply the Hopf transformation. This, then this is not rigorous calculation, just informally. So we can know that HT satisfied. So this SPD, which is called the KPZ equations, then we can have the chaotic estimate for this equation for KPZ equations. But this is not rigorous, so just informal calculation. So I think I run my talk too fast. So any question or comments? Yes.
Your solution is
mild solution.
Yeah. And in high-dimensional SHE, when you replace space-time noise by something smoother in space, then do you know the regularity?
I'm sure it's not continuous, but so if we know some estimate for the moments, maybe we know some regularity, but for one dimensional, the solution is continuous, but not differential.
You even don't know the regularity in time or in space or both?
I think should be in both. Like if we consider a heat equation on lattice, then locally it's just like the SDE. So and then you can calculate the Hausdorff continuity of the Hausdorff parameter is 1/2. So if we consider the heat equation on the lattice.
What if the initial function U0 of x has complex support? Like it has 0 at some point. Your initial function, like your assumption is the initial function is strictly positive, the infimum is positive, right? So the solution is positive. So the U0 of x, maybe you can show me the numbers.
U0 of x.
Yeah, infimum is positive. First condition. Yeah.
First, I mean this?
Yeah. So what if the U0 of x has complex support?
Then you won't have because like if you put the delta function, then you have the solution to be bounded in x. Then I think delta function is rougher than the function with complex support. Because like why we have fluctuations, like if we have if we put the complex support function on the initial data like this, then the noise outside this won't affect. So But the Laplacian will smooth the solution immediately. So I use okay, like the deterministic the heat equation. If you put the delta function, then you just smooth out immediately. Right. But here, if you put the function with compressive forward, then you can think that the noise outside this won't affect here, because there is nothing to smooth out zero. So for stochastic heat equation, I think the solution, even maybe you have probability that you have very high temperature, high potential here, then it smooths out. I think the question are asked by Van Ross and Scale and Corey. So any questions? So in that I would to say, so that's why I say the solution is sensitive to the initial data, because if your initial data is a delta function, and for fixed t your solution is bounded. But if your initial data is a constant, then you have a very high peaks.
So let's give